3 at a time. The RS-27 is still firing. Then we separate first and second stage, and the fairing comes off. And again, we'll have 2 firings, and then we'll separate the spacecraft into its intended orbit. Back to you, George.
Right, thank you, Chris. We'll go now to Kevin Grady, who is the GLAST project manager from the Goddard Space Flight Center. Kevin.
Thank you, George, and good afternoon, and welcome again to this pre-launch briefing for the GLAST mission. As Dr. Morse mentioned a few moments ago, GLAST will provide scientists an unprecedented view into the high-energy universe, an opportunity to observe some of the most dynamic and powerful forces in the universe. Could I have the first graphic? The GLAST observatory will fly in a low inclination orbit, approximately 300 nautical miles above the surface of the Earth. It will, in its orbit, roughly around the equator, it will go as far as 25 degrees north and south of the equator. Unlike many telescopes that have a very narrow field of view, the GLAST observatory has a very wide field of view, comparable to a person's vision. This will allow the GLAST observatory to view the entire celestial sphere every 3 hours. Could I have the next graphic? GLAST will utilize 2 significant on-orbit capabilities, the NASA Tracking and Data Relay Satellite System and the Air Force GPS constellation. The GPS constellation will be used for orbit position and time, and the Tracking and Data Relay system will be used to uplink commands to the spacecraft as well as downlink the science data. The science data comes down to the ground via the TDRS system and is routed to the Mission Operations Center at Goddard Space Flight Center. From there, the science data is extracted for the 2 instruments, sent to the instrument data processing facilities. There, the higher level science data products are produced, sent back to Goddard for distribution to the general, the broader science community. Next slide, please. Here you see a graphic of the observatory as well as a picture of the observatory on the launch pad. The large rectangular object at the top is the large area telescope. This is the hardware that takes the gamma rays and converts them into matter and antimatter particles for determining the source of the gamma rays. The observatory is close to 5 tons. So, as Omar mentioned, it's a very massive satellite. There are a number of significant U.S. and international contributors to the mission. The Stanford Linear Accelerator Center produced the LAT instrument. The spacecraft, which is the lower portion of the observatory, was developed by General Dynamics in Arizona. The GLAST burst monitor was a collaboration between the Germans and the Marshall Space Flight Center. The LAT team, in addition to a number of U.S. contributions, the LAT also had critical contributions from 4 international partners, and you can see those identified in the upper left-hand corner. Italy, France, Japan, and Sweden all had significant contributions to the LAT telescope. Next slide. Here's a close-up view of the LAT telescope. Again, there were 4 critical subsystems in the LAT. The subsystem that determines the origin of the gamma photons was developed by our Italian partners with significant contributions from Japan and the United States. The subsystem that measures the energy of the gamma photons was led by the Naval Research Lab with significant contributions from France and Sweden. The gold outer cover of the LAT telescope was developed at Goddard Space Flight Center, and it allows the scientists to discriminate between the gamma photons and cosmic background. We're now going to go to a short video on some of the recent processing activities at KSC. Here you see the trailer arriving with the GLAST spacecraft at Astrotech at Titusville. The shipping container is being moved into the high bay. Here the cover has been removed, packing material removed, and the spacecraft is now being hoisted to be placed on its INT stand.